Welcome back. In this brief lecture, we will mention some aspects of thermal management systems. This is a huge topic in batteries. We cannot provide an exhaustive presentation of this topic, but some aspects will be addressed in this brief lecture. So we've already introduced a cylindrical battery. This is one of the common battery geometries, probably which you've seen often in your NiCad battery and so on. So potentially you can increase the capacity of the battery by adding more windings. Okay, so you can make this radius larger and you can just increase the capacity of the battery. Why is this not done? Okay, often the cylindrical cells are rather small in terms of radius because of the heat removal issues. This is the aspect we will try to unfold in this lecture. So how to think about heat transfer is in this system, you must have learned it in your heat transfer class, all chemical and mechanical engineering students especially. So heat is generated in the bulk of the system. It is conducted away, heat flux is conducted away, and heat is removed by convection from the surface of the battery, right? So the way to model this is via simple conduction 1D equation. Why is that? Because we assume that the temperature variation is only along the radius. There is no variation in this direction. There is the axial direction as well as the theta direction. The only variation is along the radius. So it eventually becomes a 1D problem that you must have solved in your heat transfer classes, especially when you are thinking about heat transfer in fins and so on. So this quantity indicates the heat that is generated per unit volume, heat generated per unit volume. That's why there are 3 primes. This is the conductivity. And then this is just the in cylindrical coordinate, this is the relevant equation. So the next thing to address is the boundary condition. So there are 2 boundary conditions that are of relevance here. At the center of the battery, because of symmetry, dou T by dou R should be 0. Again, this you must have done in your heat transfer class. And you assume that at R naught, that is outer radius, this is the inner radius. So at the outer radius, one way of establishing boundary condition is that the temperature is equal to the ambient boundary temperature, ambient temperature. Okay, so that is one way of establishing the boundary condition. So there are 2 boundary conditions. You can easily solve this problem. You must have done it in your heat transfer class. This is the solution. You can also have an alternate boundary condition. Supposing at the outer radius, the temperature is not equal to the ambient temperature. You may use certain convection equation. If you know the convective heat transfer, the flux that is conducted via the battery gets removed by convection. You can also establish such a boundary condition, in which case usually the temperature at R naught is more than the ambient temperature. So that only changes certain things of the analysis, but the overall trends does not change. So we'll use this simpler boundary condition. So what are the important features? There are 2 important features. First important feature is if you discharge the battery at a faster rate. Let's say you are increasing the discharge rate from 1C to 2C to 3C. What happens? In all the 3 cases, the temperature at the center, okay, or temperature inside the battery is greater. Okay, so there is a temperature drop as you get to the outside of the battery. So as the discharge rate increases, the temperature inside the battery also increases. Not only inside the battery, the overall temperature increases as you discharge the battery at the greater discharge rate. So this is the critical thing. You do not want very high temperature inside the battery because that may lead to fire and so on. So if you have greater radius, the temperature inside the battery is going to be higher, especially as you get to the center, the temperature is going to be higher and higher. So even though there is an advantage in increasing the capacity, you do not increase the radius because of this temperature distribution. So the heat removal from the inside of the battery to the outside becomes harder and harder as you increase the radius of the battery. So there is a trade-off. So given the thickness of the winding, that is delta, L is the overall length of the winding, right? So this is just from geometry, you can get this. So there is a trade-off. Even though you can increase L to increase the capacity of the battery. What do you mean by L here? So let's get back to the figure. Okay, so this winding, okay, this length of this tape that is wound around the central axle, that is L. The greater the L, greater is the capacity. So, but as you increase that, your R, that is the radius, also increases. There is an inner radius and radius also increases. Okay, so if you see, this is the inner radius, and as you, the outer radius also increases as you increase L. So even though you have the advantage of increasing the capacity by increasing L, you don't want to be doing that because your maximum temperature also increases. So again, the same trends are followed. What is being displayed? Greater the discharge rates, maximum temperature is greater. So as you can see, the maximum temperature is greater, or the overall temperature inside the battery is greater. In addition, when you keep on increasing the capacity, okay, so the temperature differential also keeps increasing. That is, the temperature difference also keeps increasing. So you don't want to keep increasing capacity because the highest temperature will also increase. So as you increase the capacity, this is indicative of L, right? So the maximum temperature keeps increasing. You don't want to do that. So there is another aspect which is different from this aspect. This is called thermal runaway. This will be taken up in the next lecture. Thank you.